Hello folks, so continuing where we last left off, this video will deal with looking at specific heat capacities for elements and compounds and the like. Now that we have a good concept of energy and heat flow, or at least hopefully we have a little bit more of one, now we can look at some of the ways we actually start to measure this. Because previously, looking at, say, internal energy is not as useful as what we're about ready to do now. So, specific heat. Specific heat is the first direct effect of heat flow within an object is that the object will heat up. If I put heat into an object, the first thing that should happen is the temperature changes. Now, mind you, if the object may expand as the temperature changes. It may expand while cooling. It may react due to changes in heat, but the first thing it always does is its relative temperature increases. The study of this heat flow into objects is referred to calorimetry. Calorimetry. Calor being the heat, and metry referring to the measurement of. Now, every object will warm or cool based on the absorption or release of relative amounts of energy. The amount of heat change is dependent on the object rather than on the, it does depend on the amount absorbed, but it does depend on the object. Metal, for example, takes very little amounts of energy to increase its temperature. That's why we cook on metal. A cast iron stove or a cast iron pan takes very little amount of energy to heat up to an incredibly high temperature. It also usually has a very high melting point, which is why it is very good to cook with. Organic liquids and water are often difficult to heat up, and of course they're limited by their melting or boiling point. So like we might use cooking oil rather than water because like oil has a higher boiling point. But water takes a lot of energy to boil, a lot of energy to heat up. The pan that is cooking the spaghetti is a lot hotter than the water in there because it can heat up to a very high temperature very easily, and then that heat from the pan is then must be slowly transferred into the water, and it will slowly go up to a boiling. But a new compound dependent constant that we're going to use is called specific heat. We're going to use this as the little c. Little c. Little c is the specific heat or specific heat capacity. The units of this are in joules per gram per temperature. Typically we use degrees Celsius or Kelvin. Now there is a reason why it doesn't matter whether we use Kelvin or Celsius, because Kelvin or Celsius, we're going to look at temperature flow as a change. And going from 0 degrees Celsius to 100 degrees Celsius is a change of 100. Going from 273 degrees Kelvin to 373 degrees Kelvin, which is the same temperature in Celsius, is still 100. So it doesn't matter whether you use Celsius or Kelvin, the answer is still the same. But it's joules required to heat up 1 gram of object by 1 degree Celsius or Kelvin. Now, it is also possible to convert that into a molar heat capacity, where instead of looking at the energy to heat up 1 gram, it could be the energy to heat up 1 mole. And we can convert the two. The heat capacity of carbon would be whatever, but then to turn that into a mole, you simply have to know that there is 12 grams in 1 mole. So you'd factor that in. But the units, as I said, are joules per gram C or joules per gram Kelvin. And the magical equation we need to use is called Q equals mc delta T, or MCAT, like the doctor's exam, the MCAT. The mass times the specific heat times the change in temperature. So how much heat does the amount of heat applied is going to be relative to the mass of the object we got to warm up, how easy it is to warm up, times the change in temperature. How much do we want the object to warm up? Do we only want it to warm up by 10 degrees, or do we want it to warm up by 100 degrees? And the other version is just looking at the moles times the molar heat capacity. But just note that as all is said and done, joules per gram Kelvin times grams times Kelvin just gets us unit of joules, which is the units we use for heat. So Q is our heat. Okay, so looking at this, how much energy is required to heat up 4 liters of water, but from 25 to 100. And we need the heat capacity of 4.184. And then I ask 5 kilograms of tin, 25 to 170, and its heat capacity is 0.22. Okay, let's go look at these problems. Simplest problems really in the world. Breaking it down. Q equals mc delta T. The mass of water, 4 liters of water with a density of 1 gram per 1 milliliter, means the mass of water is 4,000 grams. The heat capacity of water is given at 4.184 joules over grams Kelvin. And I'm going to go ahead and convert these into Kelvin. So we have, and the temperature change is 373 Kelvin minus 298 Kelvin. Right there, you should be able to say 25 to 100 is 75. If I do this, this is going to be 75 Kelvin. 75 Kelvin, grams. So how much energy are we looking at for water? We have 4,000, 4.184, and 75. It's a really big number, but this is joules. 1255, 200. If I convert this, that's joules. I convert that into kilojoules. That's 1255 0.2 kilojoules, or 1.2552 megajoules. Don't really matter where we put the decimal. We just want to be able to compare. Well, what about tin? Well, tin has different numbers. 5,000 grams. That's 5 kilograms. Heat capacity of 0.22 joules per gram. I'm going to say degrees C, make my life a little easier. And the temperature change is 170 from the same 25. So I'm heating it up to, instead of 75, I'm heating it up to about 145 degrees. 145 degrees. So, doing that math. 5,000 times 0.22 times 145 breaks it to 1,595 joules, which is 1,595, well actually, 159.5 kilojoules, or 0.1595 megajoules. So not even 1 megajoule. Much, much smaller, despite having to heat up more and to a higher temperature. Heat up more to a higher temperature, it's still way smaller. So it's the basic idea that metals take a lot less energy to heat up. Now, how will we measure this? It's all well and good to say this is the heat flow. Well, to measure this, we need things like a calorimeter. We'll talk about this in a second. But so calorimetry measures the heat transfers by measuring the temperature changes. It's a simple idea that if energy is conserved, the heat in the universe, which is a change, is zero. If there's nothing outside the universe, no heat can flow out of it. The heat of a reaction has to go somewhere. So if that's the case, if I look at the heat change in a reaction, it's proportional but opposite sign of the heat change of the solution that directly surrounds it. If I look at the direct effect of these atoms reacting, the liquid that acts as the solvent or the buffer around it will absorb or lose heat based on the reaction. So, if we measure the temperature change of the surrounding solution, we will know the heat flow into the system. But the key feature is that the system plus the surroundings must be zero. Now this is true. This is true regardless of how you measure in the system or surroundings. Whether we're looking at the QP, which is the heat at a constant pressure, QV, the heat at a constant volume, or just a Q calculated via calorimetry. One of these will always be calculated via calorimetry, but the other might be a QP or QV. And the idea is that these are still all interrelated. So breaking it down into how do we actually measure this? We will use a calorimeter. A calorimeter is a thermally insulated reaction vessel that it either is held at a constant pressure or a constant volume. That these can be used to measure a specific heat of an unknown reaction, of an unknown substance. You can measure the enthalpy of a given reaction or the internal energy of a given substance. So, what does it mean? Like, if I find a new metal and I want to find out the properties of it, well, you can use a calorimeter to find that. If I want to test a new type of reaction and I want to try to quantify the energy of this reaction, I can use this. Or I have some substance and I want to find out how much energy is stored within it, I can use this as well. So a constant pressure calorimeter is one that we'll use more often than not. It's a vessel that is open to the atmosphere, so air is allowed to exchange. Could be as simple as a covered coffee cup filled with water. A hot substance is then dropped into the cup, or a solid is mixed into the water, and the change in temperature of the water can be directly measured. Now, if I'm measuring the heat capacity, we're looking at the energy lost, the energy of the water divided by the Q equals MCAT of our reaction. So we need to know how much of our unknown substance we measured and its change in temperature. And we can compare that to our water. Basically, if I drop a hot object into cold water, the cold water will warm up and the hot object will cool down until they both reach a equilibrium temperature. So it might be the hot object was at 100 degrees and the water was at 25 degrees, and maybe they both ended up at 38 degrees. And so the objects cooled down from 100 to 38, and the water warmed up from 25 to 38. And they met there, and we can figure out the heat capacity based on that. Or if I'm trying to find the enthalpy, all I need to do is find out how much heat did the water gain, and then divide by my moles of unknown to know of how much reaction occurred. How much reaction occurred? What is the enthalpy for that? Well, a constant volume one, which is called a bomb calorimeter, because technically if the pressure were to build up too high, it would explode like a bomb. It's an enclosed reaction vessel that insulates this with a layer of water. A combustion reaction is initiated, and the water temperature is measured. This is how you could find out the calorie count of foods. You essentially fully combust them in this chamber, capture all the heat as a change in water, and measure that. However, the heat capacity of the calorimeter must often be accounted for when using these things. The calorimeter itself will absorb a small amount of heat, and so we have to take that into account when we're doing this. However, once that is known, it is assumed to be constant for every further reaction we may do. Okay. So, hypothetically, this is the most challenging problem we got of this type. If I heat up 50 grams of iron ball bearings by 100 to 100 degrees, 100 degrees, and I drop them into 10 mils, which is essentially 10 grams of water at room temperature, 25 degrees. The final temperature of both is 51.21 degrees Celsius. If the heat capacity of water is 4.184, what is the heat capacity of iron? So how do I go about doing that? What do I need to do? What do I need to do there? Okay, we're setting two things equal. That the Q of water must equal negative the Q of iron, because iron is going to cool down, water is going to heat up. The sign here is going to keep this in check. The heat of water is going to be the mass of water, heat capacity of water, and the delta T of water, which means we have 10 grams times 4.184 joules per gram degrees C times its change in temperature, which it went from 25 to 51.21. Let's find that first. So 10 times 4.184 times 26.21. How much did the water heat up by? It gained this many joules of heat. Well, the Q of iron must thus be negative 1096.6 because it lost that much heat. So that leaves us with, okay, so what is the heat capacity of iron? Well, the heat capacity of iron is Q equals mc delta T. Well, negative 1096.6 equals mass. We said 50 grams of iron. We don't know the C, that is our unknown, and the temperature change is 100. Well, we started with 5121. We started with 100 and went to 5121, which is 48.79. So negative 48.79. So if I take our negative 1096.6, divide by 50, divide by negative 48.79, we get the heat capacity of iron as 0.4495 joules per gram degree C. So that is our heat capacity of iron. We found out because the iron cooled down a lot more than the water heated up, it has a heat capacity that is much smaller. So that is this portion. The next video will have to do with calculating enthalpy of reactions. But this is one thing we can do right away.